Hi there everyone, and welcome to a brand new unit. So today we're going to be starting our unit in piecewise functions. So we should all be on the very first page. That looks like this: continuity versus discontinuity. So I am just reading right here from the text. One of the most important properties of the majority of functions that model real world behavior is that they're continuous. All right, so for those of you guys that are going to be going into calculus next year, this is really crucial. And even if you're not, this is still going to continue into our lessons in pre-calculus. But I'm getting you guys a little bit of a head start on the terminology, so it flows better when you're in class, things like that later on. So generally speaking, okay, if a function is continuous, there are no breaks in the graph at any given point on the function. So we are going to look at the following different graphs, and this is all terminology, which you will be responsible for knowing, of whether something is continuous or discontinuous, and when it's discontinuous, why? What does the graph look like? What does it model? So for the first graph that I gave you guys here, notice how, let me draw better. There are no breaks in the graph. Nice smooth curve, okay, no breaks. But if I look over here, notice I have a hole. There's a point plotted up here, and then I continue back on the graph. So we call this a removable discontinuity. There is a hole in the graph. Even though there was a point plotted up here, it doesn't matter. There's still a hole in the graph. Similarly over here, this is also a removable discontinuity. There's a hole here, and then the graph continues. There's a break. Okay, again, continuing on, if I look here, I have a jump discontinuity, right? So I jump from this open circle to a closed circle up here. Look at all this space in between here, and then I continue my graph. So I had to pick up my pencil. And then here we have an infinite discontinuity where there's an asymptote where x equals a. So at x equals a, there's a vertical asymptote. And again, notice how I'm going towards negative infinity in one direction, but I have to stop at some point because I need to get up here where I'm going from positive infinity towards whatever this value is, where the horizontal asymptote is. Okay, so those are just the different graphs of what it looks like to be discontinuous. And the first example was a continuous function. So really important vocabulary here. I'm introducing it early, that way we're prepared, especially when we get into our rational functions unit. All right, so just moving on, let's just take a look at all these cases individually. Now, you do see I have limit notation here. Don't freak out, okay? We will be getting to this at some point in the year. But let's just start with basics here, okay? So the graph to the right, we can see is continuous. So I'm breaking this down now individually. It's continuous. There are no breaks or holes in the graph, right? There are no breaks. Looking ahead of what we're going to talk about come the month of May, we're going to be talking about limit notation. So really all this means, because I don't want you guys psyching yourselves out, this is just saying that this function is continuous for all values of x. So let's just say a was here. Let's say a was here. Sure, like when x equals a, right? Maybe I have an a value here. At any point on the graph, no matter where we approach this value for a, there are no breaks. And again, we'll get into what this notation really means starting in May. Okay, but just to give you guys an idea, when we calculate limits, okay, again, I'm just introducing the terminology. We're not going to get very into the depths of what limits are. But just so you do know, when I calculate a limit of a function, we check what it looks like from the left and from the right of that x value, okay? So using notation, a limit exists if it approaches that same value from the left and from the right. So maybe, let's come back up to this example here so I can, actually make sense of this definition for you. So I'm going to make up a random number here. Let's just say, I don't know, that's x equaling 4. Okay, so when x equals 4, let's say it approaches this y value of, I don't know, -2. I'm making this all up. So what this notation says is, okay, well, if I take the limit as x approaches, when x is 4, let's approach 4 from the right. Okay, so let's approach 4 from the right. Well, when x approaches 4 from the right, that's what this notation here means, of that function, we approach this y value of -2. And now if I want to talk about the limit from the left, so we have to talk about left and right. So if I take the limit of f of x as we approach now 4, let's approach it from the left. So I'm coming there, up, right there. That's where I land. I approach 4 from the left. That's what this notation means here. From the left. And this positive here means from the right. Okay. So as I approach x equaling 4 from the left, I'm hitting this y value here at -2. So because both limits approach the same y value, all right, so I just made these numbers up because they both approach the same y value, the limit exists, and we approach this value of -2. All right, but again, you guys are going to have an entire unit on limits, so don't stress yourselves out over that. Okay. All right, now let's talk about discontinuous functions. So a function might not be continuous, even if the limit exists. So if I look here, a function might not be continuous. Okay, so the graph to the right shows that it's continuous everywhere except for the hole, right? There's a hole here when x equals a. So this is called a removable discontinuity. So this is called a removable discontinuity. Okay, so because it can be patched by plugging a point or a hole here, plugging a point for the hole, so that way it is still redefined. So just to give you an example, again, using that limit notation, if you feel comfortable with it. All right, so what I have here is the limit as x is approaching a. So as I approach x equaling a, I've got a point here. So let's say, I don't know, make up a number that's -3, and this y value up here is 10. So as I approach a from the left and the right, we approach that y value of -3, but that y value of -3 doesn't equal the point right up here. Doesn't equal 10. Okay. All right, let's move on to the next graph. So again, this graph on the right also has another removable discontinuity. Okay. And again, it's removable because we can define f of a in such a way that we could plug the hole and make the function continuous, right? So I could say, all right, that was the function, but let's actually just plot a point there and fill the hole, and then that would make it continuous. All right, but this still is a discontinuous function. There's a break in the graph. Okay, now here is an example of a function, of a discontinuity that is not removable. All right, so here now we have a jump discontinuity, okay, which should make sense because we go from this open circle here and jump all the way up to this closed circle here. Okay, so there is more than just a hole at this value of x equaling a. There's an actual jump in the function. All right. And then lastly, infinite discontinuities. There is really a vertical asymptote here at x equals a. Okay, so this function is considered an infinite discontinuity because of the vertical asymptote where the function is discontinuous. All right, so we have to jump. So if I were to just give you an example, all right, so as x approaches a from the left, so let's just say, again, this is a here. As we approach a from the left, right, y goes towards -infinity. But as x approaches a from the right, so here we're approaching it from the right, y approaches +infinity. All right, so we're approaching two different values, which again means that the limit does not exist. Therefore, our function here is discontinuous. All right, we've got that vertical asymptote. Okay, so let's take a look at our graph here. So consider the graph of log x. Is this function continuous, why or why not? Well, let's see. Here's my function. There's my log function. And, well, it looks like it's getting super close to x equaling 0 because we've got a vertical asymptote there. Okay. Well, let's consider what's the domain for a log function. What's the domain? Right? And if you guys were to graph this in your calculator, you would see on the table. Well, we're getting really close to x equaling 0, but we don't actually reach it. So there's my open parentheses. And my x values are going towards infinity. All right. Well, is this function continuous? That's the question. Are there any breaks in the graph? Are there holes? Do I have to jump from one place to the other? No, you don't. So yeah, this function is continuous. Yes, f of x equaling log of x is a continuous function. Even though there is this vertical asymptote here, there's no graph on this side. Right? If I had a graph like this, maybe if I had something going on like this, then yeah, this would be a discontinuous function. But we don't have that. We're just looking at the graph that's given to us. So this is continuous. All right, it's defined everywhere on its domain. There are no holes. So just a little rule of thumb for you guys to think about in terms of discontinuity. Okay, this is not by any means like your proper explanation, but a function is discontinuous if you have to pick up your pencil. Your pencil when graphing. Okay, again, that is not an appropriate explanation though, but this is an idea for you guys to remember, whether it's discontinuous or not. Your proper explanation is, it's a continuous function. There are no holes or breaks in the graph. It's discontinuous because of X, Y, and Z. All right, you would talk about the different kinds of discontinuities. All right, so let's actually get some practice in here. So functions practice. We're going to do our first one together. And notice we're starting off with our piecewise unit. Okay, so for question 1, let's see. We want to identify all of this information here. All right, lots of different points. So first, let's figure out where the function is increasing or decreasing, constant, where it's continuous, the domain and range, and the type of discontinuity. So we've got a lot of things to identify. All right, so I just labeled it all out for us. So where is this function increasing? So as we go from left to right, where is it increasing? Well, here I'm decreasing. Okay, so let's keep in green decreasing. Here I'm increasing. And then here I'm steady. So let's write down those intervals. All right, so let's identify decreasing first. So we're decreasing from here, x is -3 to -1. So we're going from -3 to -1. Whenever we talk about intervals of increasing and decreasing, guys, they always get open parentheses for increasing, decreasing, constant, things like that. Well, let's see. We're increasing from -1 to +2. And we're constant from 2 to infinity. Okay. Where are we continuous? So where is this function continuous? All right, so let's erase this and now identify where is the function continuous. Okay, well, let's see. I don't see any holes here. Don't see a hole. Oh, got a hole here. And I don't see any holes over here. So my function is continuous essentially everywhere except at 2. So we're continuous from -3 to 2, but not including 2. So we're continuous from -3 to 2, not including 2 because there's the hole. And then from 2 to infinity. All right. Now we want to talk about domain and range. So let's see, domain and range. All right, well, again, what are the x values for this function? So if we consider just the x values for this function, we go from -3 to 2, and then from 2 to infinity again. So actually, where the function is continuous, that's also our domain. We're going from -3 to 2, unioned with 2 to infinity. And lastly, the range. Well, my lowest y value is at 0, and my highest y value here is at 1, 2, 3, 4, 5. So my range is from 0 to 5, inclusive, because I have actual points here, and I've got points here along 5. And what kind of discontinuity do we have? We have a removable discontinuity. All right, you guys are going to try question 2, again, following the same format here. And again, I do just want to include and reiterate up here on the top. Let's erase this. All right, so you only use, I'm just stressing this again, we only use parentheses for increasing, decreasing, constants of functions. Okay, I abbreviated increasing here. And we're always talking about the x values. So we're going to use the x values always. All right. And range deals with y. Domain deals with x. So just to reiterate those facts. Okay, range is really the only situation where we're including y values. Everywhere else, all those other intervals were x. This is the only one that included y. Okay, moving on to the next page. All right, so now we should be on page 5. Let's do question 4 together. All right, so let's do question 4. And again, I'm just going to write out all of those statements that we want to find. All right, so where is this function increasing? So again, as we go from left to right, where do we see the increases? So let's do this. I'll do increasing in blue. So as I go from left to right, I'm increasing here. And that's it. It's the only place I'm increasing. So we are increasing, and let's erase over this. Let's see. So we're increasing when x is negative 1, 2, 3, 4, 5. So from negative 5 to negative 4. And it doesn't matter whether there's a hole or not. Whenever we talk about increasing and decreasing functions, you always use parentheses. No square brackets here. Okay, let's see, where is it decreasing? So I see it decreasing here. And that's from negative 1 to positive 1, 2, 3. I believe that's 3. Yep. So we're decreasing from negative 1 to 3. And we're constant in 2 places. We're constant here and we're constant here. So between negative 4, negative 1, unioned with 3 to infinity. Alrighty. And now, oh boy, now we want to see where the heck is this thing continuous. Alrighty, well, it's continuous at negative 5, and we get really, really close to negative 4, right, when x is negative 4, but we don't actually reach, right, there's that hole there. So we're continuous from negative 5 to negative 4, but we have the open parentheses because there's the hole. And let's continue. So we're going from left to right to find the continuity. All right, well, we said from negative 5 to negative 4, we're continuous up until negative 4. That's why I have the open parenthesis because there's a hole. And now let's continue. Oh, but we're at negative 4 here to negative 1. But again, there's an open circle here, so that means I have to have parentheses. So we're going to union this with now negative 4 to negative 1, open parenthesis. All right, I'm going to run out of space here, so just bear with me. Unioned with, well, here I have a point at negative 1, and I'm going towards 3. So negative 1 to 3. Close those. Those are hard brackets. And then we're unioning it from, well, at 3 here, when x is 3, right? There's an open circle, so it's discontinuous at 3 and continuous towards infinity. So that's where we are continuous. Okay? And then the domain, well, the domain, we're going from, let me erase everything here. Okay, so we had, this was negative 5, negative 4, this was negative 1 and 3. Now, the domain is actually from negative 5 to infinity. So negative 5 to infinity. The reason why the domain doesn't look like this, the reason why the domain doesn't have all these unions is because the continuity is talking about the intervals where it's continuous. The domain covers all numbers from negative 5 to infinity. Even though there's an open circle here, guess what? There's a point when x is 4, negative 4. Even though there's an open circle here, guess what? There's a point when x is negative 1. So even though there are those open holes, those circles, right, I still plug the point at a different value. So I'm covering all my bases. At negative 5, I've got a value. At negative 4, I have a value. At negative 1, I've got a value. And 3. So the domain is from negative 5 to infinity. You don't need the unions. All right. And then our range, this one's like nice and easy. Our range, we're going from, let's see, negative 3 all the way up to 1, 2, 3, 4, 5. The reason why I'm allowed to say we're going from negative 3 to 5 inclusive is because even though you might be saying to yourselves, well, hey, there are these open circles here. Guess what? There's a y value in some other place, right? Even here. I've got a y value at each one of those places. So this is inclusive. And then lastly, we would just say the discontinuity is that there are multiple discontinuities. All right, and I want you guys to try question 5. All right, and again, you guys can always ask me questions, whatever you need help going over. Alrighty, so that covers continuity, discontinuity, and the different types. So stay tuned for future lesson videos and ask me questions, whatever you got.